Today's topic is subjective probabilities or Bayesianism, and it's a warning because there are in science a lot of magic words like quantum mechanics, relativity, Kalman filter, artificial intelligence, and Bayesianism, which has sort of a magic. And the problem with this is that works of less high standard try to become more prestigious by putting a stamp on it, calling it Kalman filter or quantum mechanics or Bayesianism. So this is one of these magic words, so you should be careful whenever you see something called Bayesianism. Normally it's all right, but it could be some fake or not very good work that tries to rise its standard. I mean, I'm trying to give just an introduction to the main ideas, because I think it's a very important, it will be an important field in the science of weather forecasting. It has already been, but not fully recognized. But it's controversial. Some people regard it as the solution to everything, and others that it's just a bluff. And it's important because when I want to introduce statistics, and when you enter the science of statistics, that's difficult enough because there are other equations than in physics. But when you come into statistics, you discover that there are two types, at least, of statisticians. Those who are frequentists and those who are Bayesians. So you enter into sort of a civil war that has been going on for 100 or 150 years. Now, recently there have been sort of peace negotiations, but the scars are still around. Because on one hand, as I said, the solution to everything, and there's a book which I can recommend, written by a lady in America who obviously don't know mathematics. So there's very little mathematics in the book, and you wonder if she really understands mathematics. That made me disappointed when I read the book. But then realizing what Bayesianism and the controversy is about, it's not about mathematics, it's about the philosophical interpretation of the mathematics. And the lady is very well fitted to explain that. So if you see this book, I highly recommend it because it gives a history of Bayesianism and why it has been controversial. On the other hand, the book claims that it can be used for a lot of things. So in the book, you will be told that it can prove that smoking leads to lung cancer, and who will be the next president of the US, and heart attacks causes, and who wrote the document long time ago. So there are all kind of things that it seems to be, as I said, the solution to everything. And that, of course, is not quite true. But she tells about these cases, and I think it's where Bayesianism has helped to find different types of solutions. And also because Bayesianism aligns with a lot of our thinking before we knew about Bayesianism. So the historical background to Bayesianism is a bit obscure. It goes back to this time I mentioned after the Lisbon earthquake and tsunami, when people started really to realize that there is some randomness, that in history, not everything is decided beforehand. And this man, Thomas Simpson, I think I mentioned him yesterday, was a pioneer in how to evaluate observations, to study the mean rather than try to pick the best observation. But there were also other people like David Hume, a philosopher, about is there a first cause? So like the Big Bang passed in, something started and then everything is a consequence of this first cause. And those Bayes was a priest, a bit dissident priest in England, who wrote down some ideas about this from a philosophical mathematical point of view. He died, but his friend Richard Price, who was a liberal or progressive priest, published his paper in 1763. And so my papers of our deceased friend, Mr. Byers, and then he explains what bias, and it's not easy to find out in his paper what is price and what is bias, but the consensus has been that it should be called Bayesianism and not priceism. And the roots to Thomas Bayes' theorem from 1757, but published 6 years later, is a mixture of how to treat random events, which belongs to statistics, then philosophical, religious things. Is God the ultimate cause? And everything has followed from that is some sort of autocorrelated process. And how to draw conclusions from observations. Then we can remind us that in science there are two ways to work in principle. One is to start from simple laws or rules and then deduce complexities, which you then can check by verifying observations. That is deduction. Mathematicians like that. They formulate something and then they check if that is all right in reality. The other way around is to start from observations, then try to make sense of the observations. And that is called induction. So you go from complexities observation into simple rules, preferably presented in mathematical form. And this is where Bayes' theorems comes in this philosophical. The first actually to apply Bayesian ideas without, I think, knowing about bias. There is a controversy if Laplace, the famous French mathematician, really had read or even heard about bias. But due to the problems that he faced to solve certain things, he had to, let's say, reinvent what Bayes had written 20, 30 years earlier. Another man I want to point out in this is an Italian mathematician, Bruno De Finetti, who was born in 1906 in Innsbruck by Italian parents, but then moved to Milan and Trieste and became a leading mathematician or statistician in Italy. And he died in 1985, in Rome. And Federico has given me this picture because I discovered him in a book I brought with me on the train between Trento and Bologna. So somewhere around Verona I discovered Finetti, so I couldn't make much research. But from Wikipedia, I think this, or
there is a website dedicated to
there's a website about mathematicians generally, and you can Google on Bruno De Finetti because in 1937 he published a book about subjective probabilities, Bayesianism, in Italian, that was later translated to English in the early 1970s and was referenced in the book I read. I have not been able to read him myself, but obviously he had good, interesting ideas. And when I just hastily now read through, he's very keen that we not treat statistics only mathematically, but understand the underlying ideas, exactly what I think. And then also there is an English author, A.G. Wells, The War Between the Worlds, you know, this film with Martian invaded. Now this A.G. Wells also said that understanding and knowing statistics will in the future be as important as being able to read, write, and count. And he said that in 1923, so obviously he meant our time. And this Finetti, he even said that statistics should be taught to children at an early age. So he's a man of my liking. But there were others, as I will show. But the first one was Laplace. And what is now Bayesianism? So frequentists, that was a topic for yesterday, and Bayesianism today. differ, as I said, in the definition of probability. However, they agree about I think, generally about the classical definition about tossing coins or throwing dice. And also, they agree about the frequencies definition, about the frequency of repeated events. But that is where the frequentists, at least in the past, wanted to stop. But the Bayesian then would like to include the sort of a subjective probability, which can be called the degree of belief, given information available. And that is where there has been controversy for long times. But Bayesianism is not all totally controversial, because in Bayer's paper from 1763, there is a formula which by itself is not controversial. Everybody agrees on it. It's the interpretation that has caused the debate. I will come back to this equation later on. So the classical probability is that you have a sack of marbles, white and red. And it's 10% proportion red marbles or 60%. And then a sort of typical textbook exercise is that you draw 3 of them, and then you have to calculate the probability of getting 3 red or 3 white, etc. So that is classical schoolbook statistics. Bayesian addresses the inverse probability, that you have a sack of white and red marbles, but you don't know the proportions. And then you draw 3 marbles. And the problem is now, what does this tell you about the likely proportions in the sack? So that's the question addressed by Bayesianism in principle, about the true probability, in the sense counting all the balls in the sack. Now this is now again coming back to Bayes' rule, Bayes' formula, and since many of you might not be familiar with the notation, I will explain what is A, what you call this line, vertical line, B, huh?
Y-axis.
No, it is A, huh? Well, slice, A slice, I call it slice.
In Italian we say A dato B, given B.
Yeah, that is the explanation, but just the sign.
I think it's called pipe.
Pipe, yes, so A pipe B, what does that mean? Well, here we have now all possible events. And then we have event B, a part of totality. Then we have another event, A, which overlaps B, and we call that C. And probability of B pipe A means the probability of B given A. So it means that we move and we only consider A, and then we ask what is the proportion of B inside A. That means C, the area C divided by A. So A pipe B stands for A given, as Carlo said, A given B, or probability of A when B has occurred. And it's, I think, very important to keep, because you will, as I will show on Friday, a lot of common sense breaks down when you, as I showed you with this, with my trailer on Monday from this movie Shall We Dance. about wife who thought that her husband was unfaithful because she didn't master Bayes' theorem. So, so it also has application outside science. So, and the probability of A pipe B means that the reverse the probability of A given that B has occurred. Then we only look at B and see what proportion is covered by A. That is a probability of A given that B has occurred. And nobody has any problem with this anywhere in mathematics or science. And if we now derive the equation, it's also rather straightforward. And again, I personally like to think in terms of geometrical forms. So here is now, again, event A, and probability of A is the proportion of A taken in the space of n. And then you have B, and the same applies to B, probability of B. And easily you can see the proportion between the probabilities is the proportion between A and B. And then the probability of B given A is this intersection C divided by A. And reverse the probability of A given B is again C divided now by B. And all this should be easily understood and it's not controversial at all. And then you move A and B like that. So both equal to C. And then you put them together and you make some very elementary operations like that. And then you get this formula that says that probability of A given B equals probability of A times probability of B given A divided by the probability of B. And nobody has any problem with that equation. And in many applications, it is just a way to deal with what I will discuss on Friday, conditional probabilities. The problem for 200 years has been the interpretation. So here we have again, what is highly controversial is that this formula allows that you can introduce subjective probabilities. And the crucial term is this one. So here you have probability of A. And then you have information about B in its own right, probability of B, and probability that A has occurred. And all this leads up to an update, so to say, of A. The probability of A is then transformed into probability of A when B has occurred. And the crucial term is this probability A. Where does it come from? And in sort of normal objective statistics, it comes from measurement or whatever. Nobody has any problem with that. But it can also be a pure guess or a subjective probability. The mathematics does not prevent you from putting something you like there. And then, of course, the observations B will then modify this into something new. But it will depend on what you put in here. And that is what the term called the prior, your sort of initial assumption. And the prior is the hot subject, the subject of many controversies. So that is the prior, which can be a pure guess, but of course, best is that it is a considered subjective probability based as much as possible on reason and observation, but not actually formally an objective probability. You might have a good hunch about the probability, but you cannot mathematically prove that this probability is objective. It's actually my subjective good opinion. So then you modify that into an update of probability A given B. And the objection is typically that science and mathematics should be objective, and there is no room for subjective opinions. That is fine. So, but the problem is that a lot of problems we encounter in life, in work, in science are of a type that forces us to put in subjective ideas. And weather forecasting is such a science. So when an experienced forecaster is asked, will it be rain today? And he says, well, it's not likely, but I cannot exclude it. When he said that 50 years ago, it was based only on his experience with the state of the sky, what he saw on the weather maps. Some other forecaster might agree or slightly disagree. Now we have the ensemble system, we have the MOS system. They provide sort of objective probabilities. But the forecaster is still free to look at the sky, to look at the radar satellite, and modify this, increase or decrease it, and then it becomes subjective. And if it's good or bad, as we discussed yesterday, will be decided in the long run if this forecaster is issuing reliable probabilities. But the statistical community has been in a sort of civil war about this for 150 years. And here are some notable men. On the left-hand side, frequentists, and on the right-hand side, Bayesians. And this book I mentioned by the American lady really tells you the heated nature of this controversy. They really sometimes hated each other, and I've been told also in cold Sweden, people became enemies for life because of how they interpreted this prior. But for different reasons, there seems to be now a sort of peace agreement or whatever on way. And I remember when I had statistics 40 years ago, we had a course in normal statistics, and part of that is estimation theory. So you estimate something, and then you also have a confidence interval. So let's say the estimation is plus 5 degrees and plus minus 3 degrees, from plus 2 to plus 8. And then if we said that the true value, the probability of the true value falling into plus 2 to plus 8 is 80 or 90%, because confidence intervals always were associated with the probability. If we said that the probability that the truth, the real value, falls into this interval is 90%. We were more or less smacked on the hands. Not really, but it was a death sin to say that, and you will be compromised forever in this university institution. So what we should say is that there is an 80 or 90% probability that the interval will cover the truth. So the idea is that you have, if now it's 80% confidence, you have 5 intervals of the same size, almost, and the probability that, well, they don't have to be of the same size, but they all are 80% confidence intervals. And the idea is that one of them will not cover the truth, but 4 of them will. That's how I was educated, and doing something else was sort of really a death sin. However, in Bayesianism is the opposite, which I learned some years ago. Then we are allowed in Bayesianism to talk in those terms, but then we don't talk about confidence interval, but credible intervals. So credible intervals is sort of a different thing than what it now, the confidence intervals. So here the probability to have an interval, and the probability that the truth will fall in that is 80%. So what was not allowed when I had statistics in my frequentist institution is allowed in a Bayesian institution. And now that seems to be, I said, the tension are relaxing. And that is because the traditional confidence interval was based on data decided the confidence interval. If there was small spread in the data, the confidence interval was narrow and it had a higher probability than if the data was very scattered. So the objective argument was that man is not involved, everything is just decided by nature, by the data. Whereas in Bayesianism, the probability being often a degree of belief is decided by a human and is not objective, and it is all right. But as we all know, in weather forecasting, when we deal with probabilities, we issue subjective probabilities. So we have already committed the sins and we can't do anything about that. So it was very much like Protestantism and Catholicism in the 30 Years' War, or whenever there were hot fighting. And the frequencies regarded Bayesians as sort of heretic, and Bayes' rule is wrong. But the Bayesians defended themselves that, but it works. And that was for a long time their only defense. But due to this, three types of Bayesians have developed, and you will see similarities to other cultural streaks. You have open Bayesians who declare themselves believing in Bayes' rule and applying it and advocating it and exposing themselves to ridicule or whatever. Then you have the covert, the hidden Bayesians, who apply Bayesianism, Bayes' rule, but they don't talk in those terms. They don't mention the B name, and they sort of try to hide it, but they, in practice, apply it. And then you have latent Bayesians. They're the people who haven't heard about Bayes at all, but just like Laplace, they have come into a situation where they, this makes sense. I had a good idea. So they more or less rediscover Bayesianism without knowing that it already exists. And then if you have already done the comparison with other things in society, you also have the element of coming out as a Bayesian. So it's that you suddenly, perhaps the last two groups discover that, oh, I am a Bayesian, I must sort of declare that, and then you are, so it's very non-scientific, it's more social and psychological. And as I said, the whole problem is not mathematical, it's how you interpret this prior term. So what do we need?
Telling it to your parents.
Sorry?
The first step is telling it to your parents.
Well, I think we will leave that, but it's difficult to not make the comparison. So why do we need Bayesianism? It is to allow those subjective probabilities that we cannot escape from. They are there, unavoidably, and we must find a way to treat them. And then also, it has turned out that they have a mission because frequentists tend to be overconfident, and I will give examples of that later. And also, it allows you to update preliminary statements. It's very sort of, you don't have to do everything again, you can update an existing estimation. And one of the Bayesians, American, formulated the problem in a nice way. It's far better having an approximate answer to the right question, which might be vague, than to have an exact answer to the wrong question, which might be very precise. And that also applies to meteorology, where you have sometimes very exact statements about 3.5 millimeter rain in 5 days' time, and instead of some vague that it might rain, which sounds less impressive, but actually might be more honest and closer to the reality. So this is a declaration from Bayesians why they are right, even if they don't fulfill certain expectations from the mathematicians. And first I thought of having Italian football team, but I was afraid that I would be in dangerous waters, so, so I took Sweden-Denmark. So you are sitting watching a football match between Sweden and Denmark. And 10 minutes left, Sweden is in the lead by 1-0. And in the room comes a Norwegian. And he offers you a bet, 1-20, that Denmark will win. And then you must form a subjective probability. You must, from this match, form a, as you can understand, a mental probability, will Denmark after all win? And then a frequentist, he will say, I can only do this if I have a record of 50 matches between Sweden and Denmark with the same team, same weather, where Denmark in the end is 1 goal back, 10 minutes left. Of course, that is impossible. So you have to sit there and think, this goal, this Swedish 1 goal, was that a Danish own goal? Or, so the Danes are playing better, they were just unlucky and had an own goal. So they will score at any minute. Or perhaps that Sweden should have had more goals, should be in the lead with 3-0 because Denmark is playing badly. So you must form a mental picture from what you have seen of the match, and then decide if you should accept the Norwegians' bet or not. And all that you cannot escape, because if you say no, you have making a choice. If you say yes, you have making a choice. So you can't escape subjective probabilities, for example, in this case. And to represent this mathematically, so you sit there and Sweden is in the lead, and you have a mental picture that most probably Sweden will win, but you can't exclude. That is so here is on the x-axis a draw in the middle. Denmark scores more than Sweden to the left. Sweden scores more than Denmark to the right. And there is a chance that Denmark in the end will win. Many things can happen in 10 minutes in football, as you know. So now Sweden scores a goal. And then, of course, your mental picture changes. You become more convinced that Sweden will win, but of course you can't exclude that something will happen during the 8-9 minutes left of the match. So this is, in mathematical forms, what happens in your head while you're watching the last minutes of the match. And the same is true for weather forecasting. So here you have some weather and the probability of some weather happening, and you have a climatological probability. And in the current situation, you believe that something of some probability. And then you get new information, which can be radar observations, a synop station reporting something unexpected, or a forecast from the European Center or from your Heerlen model, some new information that might strengthen or weaken your previous belief. In this case, it strengthens your belief that it will happen. So the same mental process goes on in a forecast office when you constantly receive new information which makes you update more or less your previous ideas. And there is a famous meteorologist at the Met Office, doing data assimilation. He has retired now. Andrew Lorenz, you see it's not Z as with Edward Lorenz, but a C, because his ancestors come from Austria or Hungary long time ago. And here is from one of his presentations, and you see he has a similar idea about the first guess, the 6-hour forecast, and then you have information of some certainty. That is why it's not a spike, but a bell curve. And then this new information modifies the first guess into something new. So the same symbolism applies in data assimilation. Then updating of preliminary probabilities. In the book, there's a nice story about insurance, work accident insurance in the US. Because 120 years ago, in the late 1800s, there were a lot of accidents in the US among workers. There was no insurance. There was legal processes and there were debates, and it was finally made a law that companies should have an insurance policy to cover workers' damages, or when they were hurt or suffered. So it was a law and everybody had to apply it. The problem was that in the US there was no statistics of damages, of how workers were hurt by accidents. So, and it would take perhaps 10 years before they had statistics. And of course during that time a lot of accidents would happen, and it would be breaking the law not to pay compensation. So what they did, they took German statistics, because the Germans have been very careful, as you know, with the statistics. So they took over German statistics and started to apply that when they paid compensation. But of course German statistics in America is not the ideal, but gradually, with more and more cases, they updated the German statistics in light of American casualties. And that was done in a sort of Bayesian way. And it sort of shows the advantage. Instead of waiting for 10 years to accumulate statistics in a frequentist way, they started with a preliminary guess from Germany, which they then gradually updated and improved on. And then we have the Bayesian. Somebody said that a Bayesian always carries an umbrella, even if the sun is shining, because you can never be sure it might rain still. And in a frequentist world, things can, to take now the tragic Concorde accident 15 years ago. Before this accident, Concorde was regarded as the most safe airplane in the world. And in 5 seconds' time, it became the most unsafe airplane in the world. That was because first it had no accidents, but very few, relatively speaking, flight hours. Whereas a normal company had perhaps an accident, but on the other hand, many flight hours. These numbers are just made up, but you see the point. When the accident then happened, then Concorde, the frequency of accidents with Concorde was much, much higher than for any other type of airplane. Not because I would say that Concorde was more unsafe, it was because the number of flight hours made this number higher. And the same happened with the nuclear accident in Harrisburg in 1977. Before the accident, this type of plants were absolutely sure. After the accident, they were very unsure. So with the normal frequency statistics, you run in the problem of that over 5 seconds, something can change completely. Now with the accident with the nuclear plant in the US, it so happened that a group had a few years before sat down and said, what can go wrong? What can go wrong in a nuclear plant? And had actually formulated a subjective probability, very low, but still a non-zero probability that something might go wrong. And of course that subjective probability was open for attack. It was not objective, but that still it saw the possibility of something going wrong. So the change, when the accident happened, it was not a total surprise. And the same could have been done for the Concorde. What can go wrong with the Concorde after all? So that's why one other advantage with the Bayesian approach is that you never say never. You never say 0 or 100%, because things might still... I will come back to that point later on. Actually now, because already Laplace tackled this problem, and it's called Laplace rule of succession, because he had an idea, what is the probability that the sun will not rise tomorrow? And can we be sure that the sun will rise tomorrow? And we know it has done so for very long times, but that means that the chance that it will not come up is 0. So what this philosophy led to, that to avoid that you put 0 to sort of, because 0 is 0. It's not a small number, it is absolutely nothing. He said to put a small number just to guard you that this, after all, is not impossible. He introduced a formula which I will call Laplace rule. And it so happens that you will see that also in the ECN MWF ensemble. And we partly touched it yesterday with this idea about that there are some outliers, some members lying outside the plume. And I will come back to how we actually apply Laplace rule without knowing about it. So what you do, you add 2 cases. One, so in the Concorde case, in the statistic you don't have 0 over 100,000 hours. You introduce 2 more occasions, one with an accident and one without an accident. So instead of having 0 over 100,000 hours, you have 1 over 100,001 hours. And that is just to make the fraction non-zero. It's a very small number, so it has no practical consequences, but it avoids this 0. It locks, because if it's 0, it can never happen. So that is, and I will come back to this Laplace rule later on. You can also, if you don't like Laplace, you can take James Bond. Never say never. And actually in our science, there are some British who have, I'm not quite sure if they know about Laplace rule. It's Rolston and Lenny Smith, which are rather well known in the meteorological community. At least Roberto knows them. And Neil Bowler, a colleague of mine at the Met Office, who had ideas about, in the ensemble context, how to avoid the problem if there are no ensemble members having rain. Does that mean that the probability is 0? So Rolston and Smith and Neil Bowler introduced, perhaps without knowing about Laplace, I'm not sure about that, introduced equations very similar to Laplace to put in a probability for rain when there are no members having rain, just taking into account the small number of members, 50. Because when the number of members, n in this case, increases, of course the probability goes down. And in practice becomes 0, but formally not. Then controversies about the Bayesian approach. It's about subjective probabilities, but as I said, they are unavoidable. They are there, so we must tackle them. Then this about credible intervals instead of confidence intervals. But as I will show tomorrow, it's actually suggested as a way to present probability forecast. Also, again, I think not knowing about his background in Bayesian theory, but just from practical. And then also, one problem for long times was that Bayesian statistics leads to very complicated calculation, and even Laplace. Of course, he didn't have a computer, but he was not bad at doing math. Had to give up and left Bayesianism because the calculations became too complicated. But now with supercomputers and something called Markov chain Monte Carlo simulations, there seems to be now a breakthrough for Bayesian use just because the calculations is no longer a problem. Well, at least not a big problem. So that's an introduction about Bayesianism. Thank you. I have often experienced that if I want to understand something, I go back to the original paper. So I understood Rossby waves first when I read Rossby's classical papers from 1939 and 1940. And also reading Bayes' rather obscure text gave me a feeling for Bayesianism in a nice way. And it's about a billiard table. In his text, he introduces a billiard table. And note it's a billiard table, not a snooker table, because there are no holes. And then a classical experiment would be to divide this billiard table into two parts with a white line. And then you would throw a ball, and then you can calculate, as de Moivre did in the classical sense, the probability that it will land on the left and right hand, and then repeatedly on the left or right. That is the classical approach. So throwing three balls, you have here the probabilities that they will land in different combinations, right and left. But Bayes' experiment was, he stood with his back against the billiard table and threw a ball without seeing where it ended up. Then he had somebody draw a white line, a chalk, where the ball landed. And still, Bayes didn't know where that line was. And then the idea was that, and now just to simplify it, we divide the billiard table into discrete intervals. That is not really necessary, but I couldn't do in the continuous case, and it wouldn't be easy to illustrate. So we divide it into discrete. So the white line is along one of these thin black lines, but we don't know where. So if now in this case the ball lands to the left, it's a probability of 60% because the line, or the white line, is along the 60% black line. And we start by assuming that it's equally likely that the ball will land in all these different 10 or perhaps 11 intervals, no, 10 intervals. And of course that is not quite certain. It might be that those intervals closer to the edges might be less favored than the ones in the middle. That might be the case, but we haven't any information, so then we come to what is called the principle of indifference. And that is another controversial point. When we don't have any information, as in this case, about the probability of all these equal sized sections, we assume that they are equally probable. Of course, that is a weakness because it might not be true, but we have nothing else to do. And by the way, when I was out traveling for ECNWF, I repeatedly had the question, how do you know that all these 50 members are equally likely? Because that is what we have to assume when we make probabilities. And I said, well, we don't know, but we have no information which should be more or less likely. And then I was not aware of that Laplace had said the same thing 200 years or whatever earlier, that I have been using, I had got a Bayesian skeptic question, and I have answered as a latent Bayesian, not being aware of that I was advocating a Bayesian approach. So this is an element of Bayesianism in the ensemble forecast. We don't have any information about the probabilities of all these 50 members. We have to assume they are equally likely. That's why when we compute probabilities, it's actually a Bayesian approach, not the frequentist approach. Now, so we now assume that all these sections are equally likely where the ball should land. So we lighthearted assume that they are equally likely. That is the principle of indifference. And that is, as I said, about what we actually do also in ensemble forecasting. So now, Thomas Byers, still standing with his back towards the billiard table, throws his first ball. And it ends up somewhere, and he's told it came to the left. He's told that. Then he throws the second ball, and he's told again to the left. And the third ball, and now he's told it is to the right. That's all the information he's given. And then he applies his formula. And now, so what he now take now the case for, where is the pointer? Here's a pointer. So here we have Bayes' formula. And we know, let's try, what is on the probability that it will land in the 0.4, the 40% interval. There are 10 of them, so this is just one of them. Given that the ball has come to the left. So that is a question we want to answer. Probability of it ending in a specific interval, knowing it has come to the left. And that is a probability of this interval from the start, and it's by definition 0.1, because we assumed all were equally likely, each 10%. And then we also know that if now x is the interval is 0.4, the likelihood that the ball will land to the left is 0.4, again by definition. And then here we make a summation of all possible cases where it will end in the first one with a chance of 0.1, in the second one 0.1 also with the same chance. So we add up all these possibilities and it ends up to 0.55. Now we have defined all these terms, and that information is more or less what has been defined from the start. And remember that the prior is now non-controversial, because by definition the probability is 0.1, if you believe in the principle of indifference, of course. Then we get an update, the probability now that it will end in this particular one is 0.07, 7%. So the 4 is slightly to the left. So if now it has landed in the left, that is. So now we get this, and then we do that for all the different positions. And we can see here that for this 4, we have a 7% probability that the white line is there. And then we throw once more, and it's again a left. And that increases the chances that the line is further to the right, because of course if it's very far to the right, yes, oh dear, this might be might have confused left and right. Have I? So if the ends up to the left, yes, if it ends up to the left, it's more likely if the line is somewhere here. If the line is somewhere here, then of course a great chance that it will land to the left. You know, sometimes you get you get second thoughts when you have to explain. And then the third one was, well, if now the second one has not been left by right, then of course it would be equal chances. And then, not surprising, it's most likely that the white line is in the middle. That's common sense. But now the third one was right. Now you see how this, now you have a, so first of all, it is not in the extreme right or extreme left, because you both have right and left. If you only had left, then there was a large chance that the white line was actually exactly on the right-hand side. But now you also have a right, so it is somewhere in the middle of the billiard table. And this gives now the probability that it will take different positions. And again, you throw, and it's left, and that tilts this probability further to the right. And that might be intuitively understood, but now you also have probabilities. You have numbers telling you the probability of the white line being in a certain position. And now comes the controversial part. Let's take this initial after the first throw. And of course you are after where is the white line. And you had a nightmare, you had dreamt something that the line might be somewhere. So you have some idea about the white line, where it is. Very fuzzy. So you intervene. So if there was no intervention, after it would look like that. But now you intervene and you subjectively change this straight line after the first throw. You change that into something that you think is more accurate. You have a hunch that the white line might be around 60, 70%. Because this is completely hazy or subjective. But you do that, and now you have a sort of completely subjective distribution curve without any scientific basis. But now you throw the ball again, and it's left, if I remember correctly. And then what happens is now that the Bayesian formula takes your subjective dashed line as its prior, this probability of A, the controversial term, and modifies that in light of this new observation, which was not conflicting too much. And what then will happen when you throw more and more balls is that the final result, whether you intervened or not, will be the same, because data will, in both cases, converge the result to some likely position of the white line. And of course, as we all can know, after 100 throws, you don't need to be a Bayesian to know where the white line is, because it's the fraction of left and right after 100 throws. And that's where frequentists and Bayesians do not disagree. With so many trials, there is no problem. The controversy is to make these decisions with just a few experiments. So after a few experiments, it depends very much on your prior, on your subjective input. If you instead have put this peak somewhere here, then this new information left would have more work to do, and it would need perhaps more information to push your subjective evaluation, which might have been very wrong, into the right direction. But it shows the mathematical possibilities of modifying subjectively and then have data update that, because this subjective information might not have been a dream in the night. It might be based on some information which is not easy to quantify, and you want to speed up the calculations but bringing in that information and help the data to more rapidly find the result. But then there will always be a small element of subjectivism in this estimation, as it is in weather forecasting. And the proof of the pudding is in the eating. If it turns out that on average you contribute, you improve, then it's a good thing. So here is now without modification, and this is now when you intervene. But after 5 or 6 more trials, the differences will be much smaller. Then Laplace rule of succession can be explained if you now have made 4 throws, and 3 are left and 1 right. And this was one of the problems that started probability theory. 2 people are playing, and then they have to interrupt the game at some stage. And then the question is, how should they divide the money? Who is more or less likely to have won in the end? And I think that was one of the problems that Pascal solved 400 years ago, how to divide the money when the game has been interrupted. And in this case, we can assume that there are 2 players, they are throwing balls, and one is giving a euro if it comes to the right, and one is to the left, but they don't know where the white line is. And then after 3 or 4 throws, the game is interrupted, and the question is then, what are the chances that the next 2 will be to the left? So what are the chances that the next 2 will be to the left? And then a frequentist approach. And it means that the probability of being to the left is p, and we don't know p because we don't know where the white line is. So the probability of having to the left is p, and twice is then p squared. That's easy. And a frequentist would just have 3 out of 4, that's 75%. So his answer would be the probability is 75 squared. That is 0.56. However, a Bayesian would be able to use the probabilities where the white line is in the continuous, or in this case rather continuous, spectrum from 0 to 100. And through a bit, so for example, p squared is 81 for the 0.9, and p squared is 0.64 for the 0.8, 80%. So he would come up or integrate over the whole to get the probability of the next 2 being to the left, considering all possibilities where the white line might be. And then he reaches an estimate of 0.45. And this example is carefully chosen so that the frequentist approach is more than 50, and the Bayesian is below 50. So it also means that if you have a frequentist approach, you might enter into a bet, while if you take a Bayesian approach, you might avoid the bet if it's just a matter of yes and no. So it makes a 10% difference, which might be crucial. Now, these calculations are, the Bayesian ones are complicated, at least if you have to do it by hand. So then we can get some help from Laplace with his simplified rule. So here we have now 3 ways to compute it. The probability. One is to take the frequentist view, and then we can only do it after 1 throw. And then it's left, so it's 100%, and then it's left 100%, and then it's 75%, and then you have the forecast about 0.56. And then for more trials, they converge. Bias can already have a sort of initial assumption of 50% because he doesn't know where the line is, so he assumes by choice it is in the middle. And then he upstates that opinion in light of the throws and end up here with 0.48. But by introducing Laplace rule, where you add two members, one with and one left and one right, you will actually speed up the calculations and actually arrive approximately at the same solution. That's I have deliberately avoided to show you the calculation. It would carry too far, but you will find that if you're interested in books about Bayesianism. I just want to illustrate how it works, that the Laplace rule helps us to quicker reach the target with some approximation compared to using the full Bayesian calculation. And there are a lot of books about this, about intuitive statistics and Bayesianism. And when I worked at the European Center, I had this book by Stuart Sutherland, a professor in psychology, Irrationality, the Enemy Within, is how we draw the wrong conclusions from statistics, and it also gave a sort of popular introduction to Bayesianism. Then you have this Gerd Gigerenzer, which I quoted yesterday, who had 5 different degrees of determinism defined, and he has written interesting books about risk and the empire of chance. Then Nate Silver, who is an American guru, who is said to have forecasted exactly in the last presidential election, or if it was 2008, in which states Obama would win and lose. And he has published The Signal and the Noise, which is a very readable book. And then Fooled by Randomness is another good read. But the ones I would like to promote here is, first of all, Daniel Kahneman's book about thinking fast and slow, where you will find this Finnish, not a Finnish, but about a beer can costing €1.10 example. And then also this American lady who doesn't know mathematics, but still has written a good book about the history of Bayesianism, actually focusing on the essential problem, and that is not the mathematics, but the philosophy behind Bayesianism. So, thank you. I'm trying to live according to my teaching. So I'm trying to apply Bayesianism also in my daily life. And one example was yesterday. I was doing some shopping. And the lady who took the money asked me something. And I said, sono svedese, non capisco. And I sort of tried to learn Italian, but unfortunately the preparation of the course took all my intellectual energy. But I gone along a Bayesian way. So then it turned out that she knew some English. So she asked me what I'm doing in Bologna. And I said, I'm teaching. Ah, very interesting. For how long? I said, the whole week. And she didn't understand the whole week. So now I took the Bayesian. I knew that tutti means something whole or all or whatever. The whole world knows that tutti means something whole. But I didn't know what week was in Italian. So then I took a Bayesian approach. I put in a prior. I took the French word for week, semaine. So I said tutti semaine as my prior. And she didn't understand that. But then somebody else in the queue knew what I meant, so he or she told me it's Settimania. So now I have learned, so a Bayesian way, by updating my French prior to the Italian Settimania about, and I don't know, did I say the right week with tutti Settimania? Is that the whole week? People would understand that. Yeah, so that's how I use Bayesian when I sort of use priors from normally Latin or French. And then I update with the information coming back from Italians. Now, the third lecture is about, I'm not quite sure how relevant this is, but as I mentioned on Monday, I think, with these two cases where colleagues have tried to add probabilities. One in Sweden, where by doing it in the wrong way, they made the first approach worse, so that they could have avoided to kill this project, but at least avoiding making fundamental errors, adding probabilities. And the other one was this poor trainee, not Italian, at the European Center, who was given the task, impossible task, to add probabilities just from the maps. So, and I think it was it on Monday, I showed how to add probabilities, for example, in the EZWF system, but also in any other system, giving probabilities for 6 or 12-hour periods, how you can, in graphical form, find out if the probabilities are exclusive, uncorrelated, and correlated. And I suggested some approximate, more or less approximate ways to add probabilities, at least avoiding the worst pitfalls. What I will talk about now is a case when, very special case, which might or might not be of practical importance, but at least it also shows some use of this Laplace rule. So here we have now, and this will be the theme of, you have two intervals, and in the second interval there's a high chance of rain. In the first interval, it's very small, and I had just to make the clear, it's just one member forecasting rain. And then comes the problem now, if it actually is raining in the first interval, so this one single member is right, what conclusion can we then infer for the second period? And also I tried, I'm not quite happy, but it's, I think that can be improved. For the next time, perhaps I have the lecture to find out what is happening synoptically when these probabilities turn up. So one is about 2 rain areas and one missing, that is of low probability, and the other one is more or less certain. But it might also be that both are missing, and the least likely that they both hit the location. So I try to find out how would, and that might be an interesting study, both for the Bologna Cosmolabs and for the European Center, to identify the synoptic situation for some classical combinations of probability. How does the reality look like in this situation? And also, as I mentioned on Monday, I think, when you have rain from frontal systems or rain from showers. The EPS output doesn't tell you if the probabilities is from one or the other. So in this case now, you have 2% probability, 1 out of 50 members for the first period, and the next period is 70%. And just now from a formal point of view, if it's rain in the first interval, it's absolutely, so here are the three synoptic cases, where both miss, where both hit, and when one hit and one miss of these two rainfalls. There might be other synoptic situations where these probabilities come out, but I couldn't figure out. So now it means that if there's rain in the first period, just from a formal point of view, it's absolutely sure it will be rain in the second period. But I would feel nervous about saying 100%, because the first one is just one member. And the rain occurred in the first period, and then it is absolutely sure it will happen in the second period. That is applying the principles I outlined on Monday, but then I had 20 or 30 or 50% probabilities, and then I had no problems. But I would be nervous about basing 100% forecast just on the formal agreement between one member and the same member the next, because this member will have rain, but perhaps not for the same reason as it is raining. It is raining, but it might be that the synoptic situation is different to what this member actually has. So it's just a coincidence that this member has rain. So I would be nervous to do this. And it feels counterintuitive to base 100% forecast just on one member. So what I do is now I introduce Laplace law of succession, or Laplace rule. I introduce two more members, one with rain and one without rain. It's a 50-50, and of course it can be done differently, but that would perhaps complicate things. But I will just say two members of one with and one without rain. So now increase the number of members to 52 in the ensemble, in the ECWF ensemble. And that is also applying actually Laplace rule of succession. So now the probability of rain, first of all, as I mentioned before, avoids always 0 and 100 probability, 100% probabilities, and applied for few members will actually slightly modify the probabilities. So having one member with rain does not mean 2%. It means 2 over 52, which is 1.9 or something else. But not of a terrible difference. And we also applied something similar with the Talagrand diagram, which actually has 52 boxes. We count the outliers as belonging to two new boxes, the outlier boxes, which are not part of the boxes. It's sort of new members, so to say. So in some sense, the European Centre has already applied Laplace rule without being aware of it. So the European Centre, in some sense, is latent Bayesians in that sense. Also in other sense, by the way. And then these two members in both periods can be either like that, or they can be like that. So it means that one member having rain does not necessarily mean that it is rain in the next period of that member. It can be 50%. You can play with these probabilities to make the whole approach more realistic. And so now you have back to the original data, 50 members, and one has rain in the first period, also in the second, and many other members have rain. So what you do now, you increase by two new members, one with and one without, and in this more clever way. First to break up the 0 and 100% statements, and then make a slightly more or less formal application of the transition from the first period to the second. So now if you apply this and now you know it is raining in the first period. That is your input. Then you will go from members to probabilities, like that. And now you can see that one member is not 2%, it's 1.9%, but that's not a big deal. And now we are back into percentage space, and here is now rain in the first period does not mean necessarily rain in the second period, but perhaps 75%. And of course now we are in this Bayesian, we have subjectively defined these extra members having certain properties. That's why we get 75. With other definitions, where these two members, we could have, for example, 2 dry members and 1 wet, so we have 3 more members. That would give, or 2 wet and 1 dry as extra members, would give slightly different probabilities. But the point is that to avoid, the main point is not if it's 70, 80 or 60, the main point is to avoid to issue 100% probability on very weak evidence. So 75 is still promoting rain, but not as confidently as in the formal approach. And it's to avoid overconfidence, which is a general problem, not only in forecasting meteorology, but actually in life in general, that we want to avoid, to soften our statements. So here we have another case, and now the rainy member does not have rain in the second period. Then from a formal point of view, we would say, well, there is no risk of any rain because it's raining now. So there is no risk of rain in the next period. But since there are many members who actually are dry now, but they have rain in the next period, I would again feel nervous, very nervous, to issue a 0 probability forecast for no rain. Like this. So instead, I repeat this exercise, but now I add these 2 extra members with a 50-50 chance of rain or dry, and go to 52 members and calculate the probabilities anew from a 52-member ensemble. And now I get a 25% chance of rain, which of course can be debated. It could be 40, it could be something else, but the main point again is to avoid issuing a stupid 0% probability just from a formal approach of the single member. So and of course, this can also be applied if there are 2 or 3 members having rain early on, then rain or no rain afterwards. So that the problem I'm addressing is low probabilities that can easily be over-interpreted when you draw a conclusion for the next period, to sort of soften up this approach and not put all your bets that these members actually represents the reality. As I said, the reason why these members have rain might actually be for other reasons than we have rain just now. But that might be no time to look into how this member looks synoptically, if it has the cold front or warm front in the right place. So this is a way to more quickly soften up and avoid issuing unnecessary 0 or 100% forecast. And so here is a third example where the probability of rain is a fraction, and you can do the same exercise, and now you come to some probability for the next period of, let's say, 70%. And it's all based on this Laplace rule of introducing bogus members, one with and one without the event. And thereby avoid the 0 and 100% statements. Then one annoying thing with probabilities, also when they came from statistical systems like the model output statistics or any, is that here you have a typical, it's actually from the EPS, but it could be from a MOS system. You have probabilities of rain. And then you might say, assume we know that it is raining. How does that affect the probabilities downstream in time? And then there is another way to theoretically, conceptually think about this. And that brings back the Markov chains I presented yesterday. And it was actually an approach I was working with at the Swedish Met Service before I was recruited by ECNWF. A way to update. That was not ECNWF probabilities, it was from actually sort of Markov chain system, combining Markov chains and model output statistics, just enabling the forecaster to enter into the probabilities and change them and see the effects downstream. And so here we have a sequence of probabilities for 6-hour periods. And now assume that we know, either because we are there in time or because we have very strong indications for other reasons, that it actually will rain on that interval. Then, of course, the probability 6 hours later must be affected in one way or the other. And with the EPS, it's possible, but it takes some software designer to do that, to ask the EPS system, as I did, what I presented before this is actually can be done automatically. You ask the EPS system, if it's now raining on this time, what are the modifications I have to do downstream? And of course then also taking Laplace rule into account. But just to sort of show how the Markov chains can be used in this, because this Markov chains can also be applied on the EPS members. So instead of having transition of observed rain from one 6-hour period to the next 6-hour period, you can take the EPS, so the user members of the EPS from each 6-hour period and create Markov chains from the EPS. That will be sort of a link, these Markov chains throughout the 10-day period, linking in principle day 0 to day 10 statistically, the interrelation between all these forecasts. Because what I feel uncomfortable with now is that the probabilities from the EPS come out sort of individualistic for every 6-hour period. They are, of course, linked, but it does not come out in the EPS gram. In the EPS gram, they stand out as individual probability statements. And the interrelation, I think, can be highlighted and might bring out new information, at least how to add, to ask a question, what is the probability over 12 hours, over 18 hours? What is the probability that it will happen at all during a specific day? So then you can make a transition matrix of the members. And so depending on if it's rain or not in a member, it's rain or not in the same member the next period. Here I have not taken Laplace into account because I should, but the number of members are so large, so it doesn't really make any difference. But in principle, it should be done always to increase the members from 50 to 52 with this artificial addition. So, so did I press? Yes. So when I tested this, perhaps it was not the best case because it's always better to have radical changes, but with the setup of the matrices, in this case, the probability increased from 32 to 39, and in the next step, from 36 to 39, and from 44 to 45. As you can see, the impact of knowing it will rain decreases. It's largest the first 6-hour period, and then it's very faint after 12 or 18 hours, which is to be expected because the impact of the information decreases with time. And here is how this is. You can here see the matrices I have used, and they are also evaluated from the ECNWF 50-member ensembles. And in this case, I have also the known weather. It is a test from London, so I knew the weather. So I have now made, for every case, a 6-hour adjustment. So here you can see the probabilities up there are the ones coming out from the EPS, and the new ones are the modification knowing the weather 6 hours earlier. So it's just 6-hour updates. And then depending on the situation, you can see that sometimes the probabilities decrease by 5 to 10%, and sometimes even increase up to 30%. It all depends on the weather situation reflected in the Markov chain derived from the EPS. And synoptically, it means that if now a very certain rain is approaching, knowing that it is already raining will increase the probability that it will rain the next period. Or if it's a more narrow band, knowing that it already rains in the first period will make it less likely it will rain in the second, because then the front has passed. So these Markov chains are a statistical reflection of the synoptical situation, as we discussed the first day with the narrow rain fronts, where it either rains in the first or the second period, or broad rain areas where rain in the first period almost makes it certain it will rain in the next period. So it's a statistical way to describe a synoptic situation, so to speak. And that's why the changes are quite different depending on the previous weather and the synoptic situation. And the synoptic situation is sort of encapsulated in these transition matrices derived from the EPS. I can't say more. If you are interested, all this will be on the web, so you can look at it, and because, of course, it can also be applied to the Cosmolabs. There is no reason not to, that you have to have ECNWF always. Yes, that was this part. So, I'm happy to know that Bologna was early on using Kalman filtering. And I was not aware of it, but it's actually a Bayesian approach, and it explains some of the reaction, the conservative reaction I had when I wanted to introduce this. And some of the points here I already made yesterday. So I will not go into the Kalman filter mathematics except in the very final end, which I added just an hour ago about some important technicalities. No, the main point is not perhaps the Kalman filter mathematics, but what it does. And here we have an example of, on the x-axis, as before, the forecast itself, and then the error or the correction, just a matter of changing sign, on the y-axis. And we have here 4 verifications showing non-perfect forecast with a mean error. Now, is this now a flat bias or not? So I more or less repeat what I did yesterday. Now, later verifications come up here, and we could then say, aha, the mean error has changed. It has gone up. But we can also say that nothing has happened. The system has not changed its characteristics, but the systematic error is actually along a slope. So depending on the regime, we will either have no mean errors, negative mean errors, or positive mean errors. And trying to correct this with a flat bias approach will lead to that if this system learns to apply a negative bias in certain regime, if that changes, it doesn't apply for another regime, because it is a self-learning system and not a static system. So in this, the system I had running in Sweden when I left for ECWF had 4 dimensions, 850 temperature, and then adjustments from the last observation. But it was not very popular at SMHI. And then in September 1991, I had calls from Sweden that my Kalman filter system behaved very strangely. And then I said, have you updated, because in those days they picked for different Swedish location, different grid points. And they had certain numbers. And in September 1991, the UP Center had changed the resolution. So I said, it's just a matter of changing the numbers. And this didn't go through. Obviously, I was talking on a too high theoretical level, because the message that they understood was not the one that they thought that Anders' Kalman filter system that doesn't work after all, so it was closed down. But so when I come back, I managed to introduce at least this simple, which sort of takes into account both mean error and the spread, as I recounted. It's the same with MOS as with Kalman filter. This sort of 2 or 3 or higher dimensionality, avoiding the one-dimensional flat bias, corrects both for errors, make the forecast more accurate, and also modifies the spread so it becomes realistic, which is essential for ensemble approaches. And what happens now in a Kalman filter system? So here we have now the prior, to talk in Bayesian terms. We have the slope that reflects the experience from the past, the relation between forecast and the error. And the dashed line is that we are not quite certain. It's not based on 100,000 cases, so it has a certain uncertainty, this first preliminary idea. Then we have a verification that is also not certain. Not that the observation error has been made, but to what degree this observation represents the system, because it's just from a station and it might be affected by local effect that is not represented in the system. So the ideal would be rather to have an averaged over the area, as I mentioned yesterday, rather than a point. Now we have a point, and it's also a bit uncertain. And these 2 uncertainties are acting as some sort of weights. So if the uncertainty is high with the observation, this filter is less affected. If the filter, on the other hand, has a high uncertainty, it will be more affected by the observation. So the interplay between these 2 uncertainties, that depends how much this observation affects this assumed relation between forecast and error. And then, depending also on where this observation occurs, the correction will be both in A and B, both in the intercept and in the slope, A and B. And it's called the least, least action, sort of variational approach, or you can say that the system is very lazy. It doesn't want to do more work than it has to do. So if now this observation comes close to the y-axis, the most efficient thing is to lift this line a bit. And that is mainly changing A and leaving the slope more or less unaffected. On the other hand, if the observation comes far away, then lifting would be very cumbersome. It's easier just to make a little small change in B, in the slope. That would have a large effect for a more distant observation. So depending on also where the observation occurs, that it will either be a translation or a rotation of this line. And all that is done by the mathematics in the Kalman filter. Then what I had to argue constantly during my time at the European Center and before and after, that you don't really need to have experienced a temperature to actually make a rather fine correction. Because now assume that it has been a mild period. So most of the forecasts have been in the normal or in the mild regime. And then if now this linear assumption is valid, it's also valid for cold temperatures, although we have not observed any cold temperatures. We have forecast of cold temperatures. So the A and B are defined only from a long experience of mild or normal conditions. And then suddenly there is a change of regime. Cold air is coming down, very cold air, and the forecast is now in a regime where we have no sort of experience. But still, the new forecast is here, and the slope, so it can suggest a correction, which is quite different, at least, to the corrections applied the days before. So, first of all, if the corrections have been around zero or positive, this can be strongly negative. And then hopefully not too bad either. And then more observations come in, and so this was this slope, and later observations showed that it was not the perfect line, but not too far away. So it gave a reasonable correction in a regime that the system had not had any experience from, just because this linear relation covered the whole climatological range. It is not necessarily the case, but from my experience, it applies to wintertime conditions over Europe. In summertime, it might be more common with flat biases, but that is 25 years ago, so I can't say it is still valid. And this generation of A and B, now here they are called x1 and x2. It's the coefficients in this equation. If you plot them in a time series, it can be interesting that they can be related to, for example, changes in the external conditions. If you have a period of green grass, then A or B or x1 or x2 might oscillate around some value. Then suddenly snow settles on the ground. That will change the relation between the model temperature and the real temperature. So the x1 and x2 or A and B will change. Or the reverse, there might be snow in the model but not in reality. Then they will again change to take this new relationship into account. So you can actually, by plotting them, link changes, in particular abrupt changes, to changes in the external conditions. And it's important in my country because snow, which is can be of many different types. You can have light snow, fluffy snow, you can have heavy snow, wet snow, dirty snow. And the model doesn't take that into account. In the IdroMeteoClima and Hirland models, the snow are always white Christmas snow. But in reality, they can be quite different with different radiation properties that affects the temperature as well. By the way, when I was working with Kalman filter, many people said, why are you not using the clouds? Because I use the 2-meter temperature, as here, and then also 850, and then the last observation in the morning. But clouds are, of course, very important for the temperature. If it's clear, the temperature will drop in winter or rise in summertime. So why is not clouds included? Well, I said, it's because clouds are important for the temperature, no doubt about that. But what I am forecasting is not really the temperature. I'm trying to forecast the error, the forecast error. I'm trying to predict the error. Then when I have done that, I add that to the original forecast and hopefully improve it. And so far, I have not found, that the cloud or the cloud forecast correlates with the error. Of course, it correlates with the temperature, but it does not, so far, correlate with the error in the temperature. So that's why clouds, although they are physically important, can so far, what I have seen, not contribute to the Kalman filter, because the correlation with the error so far does not exist. This is a sort of propaganda demonstration I had at the European Center, because some people work in the Alps or in mountainous terrains, and that is a challenge for Kalman filtering, because the station height might be systematically given to warm or to cold temperatures, and there might be other systematic errors. So I took now observations from Munich and a grid point which I had available because I was at the SMHI, so I had not easy access to the full database at IdroMeteoClima, but I had a selection of stations, and one was Feuerkogel, I think in the Austrian Alps. So I took the grid point from Feuerkogel and applied it to Munich. And then I could very well have taken the grid point value from Munich directly. But the point was to show that if now your station of interest is in the Alp, in a valley in the the Alps, you can very well use a grid point from, because in the European Center model and in many, the valleys are not deep enough. So so what I want to illustrate is that the Kalman filter can be quite efficient. So here is now the dashed line. The blue line is night temperature, and the red is day temperature. The dashed line is IdroMeteoClima forecast for Feuerkogel, the mountain in Austria, and the balls, red and blue, are the observations in Munich. And it shows that, this is pushing my luck a bit. It's a long distance between Feuerkogel and Munich. But of course, the weather patterns with a large scale makes that a lot of things are correlated between Feuerkogel and Munich, in spite of the height difference and the temperature difference on average. And as you can see, it works quite well, that the Kalman filter corrects Feuerkogel direct model output in a sensible way to the temperature conditions in Munich. But so if you have now a station in a valley, you can very well take a grid point from the nearest grid point from the European Center model, even if that is on a completely different height and reflect more the alpine conditions. There should be a possibility to adjust that down to the conditions in the valley. And then this is more or less a repetition of what I showed for Tromsø yesterday. Here is now the EPS for Feuerkogel and the observations from Munich before filtering. And then you have, and there's a range of 21 degrees. And then after filtering, the fit is much better, and the range has slightly increased, pointing to an underestimation of the spread. Not perhaps for Feuerkogel, because Feuerkogel is in the, as far as I know, in the ventilated atmosphere, but Munich is more in a valley, in a flatland where there might be larger spread. So the spread has adjusted from the Feuerkogel spread to the Munich spread by 6 degrees, from 21 to 27. And here we have 20 degrees spread and 26 after Kalman filtering, about the same size of spread. And of course it is spread, so it's important not only to make the forecast more accurate, but also that the spread becomes more realistic, so the probabilities are more reliable. Then I repeat what I said yesterday, that it corrects, the spread correction changes over and under confidence. And I have, so here is I think now I am back in Sweden, in northern Sweden, with a sea point, a lighthouse, and an airfield in northern Sweden. And my point here is that before the filtering, so here is the forecast variance before filtering and the forecast variance after filtering. And before filtering, it was this relationship. It means that it was overstating the variability, and then after filtering, it became, sorry, it was, yes, it was overstating. So 7 should actually be 6. But after filtering, then you had a more nice fit between real and observed variability. So again, it points out that it's not only to make the forecast more accurate, but to improve the spread and thereby the probability. And here is another example from a Nordic station, which one I don't remember. And before filtering, the forecasted spread and the observed spread did not agree. But after filtering, there's an almost perhaps too good fit between spread observed and computed. And then further, now I come to something, Carlo, that I haven't told you before.
No, the question was correlated to the other lesson, to your previous.
Yes, yes.
We can go.
But it must be because I have spent hours trying to convince people about this outer. So that's why I've been a bit patronizing now. That these are very important things to keep in mind about the spread. Now, in this Kalman filter, we have a covariance matrix. The covariance matrix represents or describes the uncertainty in our estimation. And it will be more or less, it will be updated, but rather little, because in practice, it will be the last week's observations. And now I didn't tell you that. Whereas the model output statistics works with 3 or 4 years of data. They run a linear regression scheme through, and then they apply the corrections. In the Kalman filter, only the last forecast is archived. And once this forecast has been verified, and you have got an error of the last direct model output, Hirlam, your system or ECWF, then this forecast is purged. So there is not much archiving in this. It just relies on the last forecast and how well it fitted the observations. And some people have been nervous about that. So as a compromise between having 2 or 3 years of data in the MOS and just 1 in the Kalman filter, they have systems where they have the last 3 weeks of observations dragging along. So every day they purge the oldest observation and put the forecast and put in the freshest. And then they run a regression scheme through this 21-day data set. And this is a bad compromise. It's worse than the MOS, it's worse than the Kalman filter. But people, and I have understood this only recently, it is Bayesian approach that scares people. People want it is a frequentist approach that they have these 21 days of data, can look at it and run regression through it, and then they feel safe, although this system is clearly worse than both the alternatives. So now this single observation with its uncertainty plays with the uncertainty of the line. And it's a covariance matrix, 2 times 2 covariance matrix. And again, I didn't have time neither in Sweden or later at the Met Office to make use of this covariance matrix because it represents the uncertainty due to small grid, subgrid uncertainties. And they, of course, should be included in the spread estimation. And there's actually a mathematical way to do this. So, before I come to that, I had some debates with people at the European Center. And it turned out that they do not always understand Kalman filter. And then somebody, but Anders, now you are wrong because they are using Kalman filter in Kalman data assimilation. But those Kalman filters are not real Kalman filters. They are simplified Kalman filters. Whereas in my system I have values in all 4 points. They only have values along the diagonal. But that is because their Kalman filters are not 2 times 2 or 3 times 3 dimensions. It's millions. So their matrices are millions times millions. And then, of course, they cannot computationally cope with that amount of data, so they only consider the diagonal of the covariance matrices. And so one could say that my Kalman filter is a real Kalman filter, and the ECWF or NCEP are not real Kalman filters. And it's important for another reason I will come later in this lecture. So then there is a mathematical way, and I will not go into it because, well, I still have 6 minutes, but I need to say something more. But you can find this out. You can actually use this covariance matrix to compute an additional uncertainty due to small-scale variability. So when you Kalman filter for the cosmolapse temperatures, apart from this large-scale change in the variability I have talked about today and yesterday, you can also add a little contribution from the small scales described in the covariance matrix, which will further increase the spread, which is normally too small. So probably it will further improve the system. So here are the details, how this can be done. And in this case, there would be an increase by ½ degree in the standard deviation of the forecast. Now we come to something I put in only this morning, because I was generous and I handed out my Kalman filter program to people. And sometimes I got a response that, but Anders, the way you treat your covariances, when you update your covariances, is not according to the books or according to what we do at ECWF, Met Office, or wherever. And that's, well, I said, that might be the case, but it works fine for me, and it's computationally very efficient. So if you save some nanoseconds, what's the big deal? But then I became aware during my time at the Met Office that it was a more fundamental problem. And it's called the Joseph form. And remember the Joseph form, because here is now, I don't intend to go into the details, but this is my update of the covariance matrices. So irrespective if we understand that or not, it's quite different from what you see is used in most textbooks, and also by, as far as I know, the data assimilation people at the Met Office, the European Center. And of course, when you are Anders Persson against the European Center, Met Office, and many books, of course, Anders Persson will lose. And people will change Anders Persson's program from his covariance treatment to the one that is sort of promoted by the big centers, Eugenia Kalnay in her book about NWP, etc. But these are applicable in data assimilation with this million dimensionality of the matrices. Whereas mine applies to these small Kalman filters. It turns out that, which I was not aware of, if you apply this one to 2 or 3 or 4 dimension Kalman filters, you will run into numerical instability. And I actually found that people who had deviated from my program and taken the sort of textbook or the data assimilation Kalman filter had run into computational difficulties and blamed it on the Kalman filter. Our Kalman filter is bad, and put it in the bin. Now, the solution is to realize that this is called the Joseph form. I don't know who Joseph was. It was not the biblical Joseph. It's some American or whoever, or Israeli. So this is the Joseph form of this covariance treatment, and this is the non-Joseph form. And again, you are lucky in Italy, because there is a paper from Milan, which I found on the web when I was at the Met Office, that discusses this Joseph form and why it makes the computational more efficient. It is slightly longer, but the computational efficiency of Kalman filters are very high. So perhaps if it takes a few nanoseconds more, it doesn't matter because it's quick anyhow. So this paper by Marco Lovera, I think it's not a fresh paper, from a Polytechnic school in Milano, discusses this Joseph form. He's not the only one, but I found this the most illuminating paper. There's a lot of wonderful equations for those who want, and also examples of why numerical instability occurs when you use the wrong type of covariance. So that is a bit technical, but you will find, if you are interested, the details if you Google on Joseph form or take up this paper. And the important thing is to realize that there are different ways to deal with Kalman filter, which are determined by the application. Thank you.